on? Is that working? Okay, great. Thanks so much for the introduction and the invitation. It's always nice to get out of Chicago during the winter. Of course, winter is 80% of the year, so maybe that's not a sustainable thing. But anyway, great to be here. I also have to thank the organizers for having Carlos, Mark, and Bruno give talks before me, because they gave a very beautiful introduction to a lot of the things, and now I don't have to define. Okay. Okay, so I want to talk about a question that's a fairly simple question that's very much in the world of sort of the topology and analytic geometry of complex algebraic varieties, and so very much sort of in the world that benefited from much of the ideas. Let me start with a couple reminders. So an analytic space X in Stein is a closed analytic subspace of F space in the end. This is with the small caveat that we need to assume that the embedding dimension is bounded. And an analytic space is holomorphically convex if it admits proper morphism to a Stein space. Okay? So both of these conditions are about existence of global holomorphic functions. Being Stein means that you have global holomorphic functions that separate points, and holomorphically convex means that you have global holomorphic functions. At any point, there's a global holomorphic function that's non-zero at that point. And somehow you can't separate points. You can separate points up to sort of proper ambiguity. There's compact spaces that you can't separate. And okay, in the set theorem, but not a definition. Or a simple definition. Well, there's many definitions of Stein. I don't know if there's a simpler one. But it's simple. All right. That's not a simple definition. Well, it's pretty simple. They're closed analytic subspaces to the end. I don't know. Well, if it has, if it admits, it's not is, it admits. And these are definitions that apply to abstract manifolds. That's true. That's true. The actual definition is about sort of being, if you like another definition, maybe you'll think this is a theorem, the existence of a strictly closed harmonic question. Anyway, okay, let me not go into full detail about that definition. And Shafarevich in the 70s asked the following question, which is a bit outlandish. Let X be a smooth projective complex algebraic variety. Is the universal cover holomorphically convex? In other words, does the universal cover always have enough global holomorphic functions to separate points up to this sort of compact ambiguity? And like I said, when you first see this, this is a bit outlandish until you start trying to think of a counterexample and realize you can't think of any. Let me give some first examples that show that, well, maybe there's something here. So, well, okay, example 0 is not so interesting. If X is smooth projective and simply connected, or in general, it's finite fundamental group, then of course the universal cover is holomorphically convex because it's compact. Okay? The Stein space appearing in the definition is just a point. Okay, so the interesting thing is if we're dealing with smooth projective varieties that have infinite fundamental group, because then we might lose compactness on the universal cover. But here's another example. So X is smooth projective and K-trivial. So it's the first term of its tangent bundle is numerically trivial. Then the Bogomolov decomposition theorem tells you that up to a finite total cover, X splits into a product of three irreducible types of K-trivial varieties, an abelian variety, what are called hyperkähler varieties, and then sort of strict Calabi-Yau varieties. And the second two types are simply connected. So in particular, it implies that the universal cover is holomorphically convex, because in fact it's a Stein space cross a smooth projective variety. Okay. Here, the map of Stein space is not so interesting because it's just a projection instead of the splitting maybe you don't expect in general. Okay, so I'm going to give a very important example 2 in a second. But before that, I want to talk a little bit about the history of some of the work that has been done on this conjecture question. So in the 80s, the sort of study was initiated by the work of Napier and Gurger Shastri, who were getting examples for some algebraic surfaces. So in the 90s, Kolar and Campana introduced the following idea, which was sort of gave a way to attack this question coming from algebraic geometry. And the observation is that, okay, so suppose X is our smooth projective variety, and its universal cover does admit a proper map to a Stein space, which I'll call Y. Well, now we can take the quotient back down, mod out by the action of pi 1, and that means that X will map to a complex analytic space Y, and because everything is proper, Y in fact will be algebraic. And this Y will have an interesting property. Its fundamental group will be large, which means that for any positive dimensional subvariety, the image of the fundamental group of the subvariety in the ambient I1 is infinite. And the reason for that is simple. If it weren't infinite, then up to a finite cover, it would lift all the way up to the universal cover Y tilde. So you would have a compact analytic subvariety of Stein space, and since Stein spaces have lots of global holomorphic functions, that would be bad. I mean, enough to separate points. Okay, so the idea of Kolar and Campana is rather than trying to construct the map upstairs from X tilde to Y tilde, try to use algebraic geometry to construct this map X to Y, where Y has this large fundamental group property. And in fact, more generally, in any subgroup of the fundamental group, H, you can try to construct a contraction X to Y that kills off all the subvarieties who have a finite image on fundamental groups in pi 1x mod H. Okay? And they don't produce such a map, but they produce sort of a rational map that satisfies this property at a very general point by sort of quotienting out by an appropriate equivalence relation. So you should view the construction here as very reminiscent of like the MRC quotient or rational connectedness. Okay, so now let's go back to that promised example 2. Example 2 is going to motivate most of what I'm talking about today. Suppose that X is a smooth projective variety that has a Z local system B, which underlies a polarized variation of Hodge structure, as we can see earlier today. So, for example, you could take a smooth projective family W over X, and the local system you could consider could be the local system formed by the degree I comolecule particles. Okay, well now there's a period map. So this variation of Hodge structure means that there's a filtration that's moving inside the associated flat bundle in a particular way, and we can track the filtration with respect to a flat trivialization. So that gives us a map to D, a moduli space of framed Hodge structures, modulo this integral framing group, G of C. And this map, X, is compact, so this is a proper complex analytic map. It has a well-defined image and results of, well, I'm not sure if I'm fully getting the history right here, but certainly Griffiths and Arden, the things should show up there, show that Y is in fact algebraic. Maybe I should also put Gaga in there. So Y is an algebraic variety. Moreover, the local system, and in fact the variation of Hodge structure, is pulled back from Y because it somehow lives universally on D mod GZ, although it's not a variation of Hodge structure on D mod GZ because there are non-Griffiths transverse tangent functions. And moreover, the local system W on Y has the property that it's large, meaning it has infinite monodromy on any positive dimensional subvariety of Y. Okay? So this map X to Y has contracted all the subvarieties on which the monodromy is finite. Why is that? Well, this is for the key reason that an integral polarized variation of Hodge structures is isotrivial, meaning the Hodge filtration is flat, if and only if the monodromy is finite. Okay, so this map, the map that sends, a subvariety of X gets sent to a point in the classifying space if and only if it's a trivial, but that turns out to be the same for the local system having finite model. We contracted subvarieties with finite model. Okay. Moreover, we get what I'm calling Y tilde W. So this is the minimal trivializing cover of Y. Sorry, the minimal cover of Y that trivializes W. Okay, it's the cover corresponding to the quotient of pi1, which is the image of the monodromy representation. And that lives inside of D. It's a component of the inverse image inside D, in fact. And it's Stein. And that's because, going back to the second definition we gave, Steinness can be checked by finding the strictly pluriharmonic exhaustion function. And D has sort of negative curvature in the transverse direction, going back to early work. And you can find such an exhaustion function. And because our map F was proper, that means if we also base change X, and you look at the minimal trivializing cover of X tilde V is holomorphically convex. Okay, so we're starting to get a lot of the same things that we've been talking about in connection to the Shafarevich question are showing up here. So this suggests, So in particular, if the monodromy representation of V is faithful, then we can conclude the universal cover is holomorphically convex. Okay? And that's just because if it's faithful, that means this minimal trivializing cover is in fact universal. There's some trickiness here in general, let me say, because Steinness behaves well passing to the universal cover, but holomorphic convexity, of course, is not, because we might unwrap the fibers of the proper map and lose compactness. Okay, so the fact that we get everything we want in this case of an integral variation of Hodge structures suggests that we should use non-abelian Hodge theory to be able to say something about this question in the case where we have a local system, but which is not an integral variation of Hodge structures, because non-abelian Hodge theory connects sort of all local systems in some way to variation of Hodge structures. More on this later. So building on, it was Simpson who first developed this theory, but building on some other work of Simpson and Corlett and Katzarkov and Ramachandran, this led Eyssidieux in 2004 to prove the following theorem. So if X is smooth projective and V is a semi-simple complex local system, then there's an algebraic map X to Y, which has the property that the local system is pulled back from Y. The local system on Y is large, so we've sort of distilled out all the subvarieties of X along which the local system has finite monodromy. And the trivializing cover of Y, the minimal cover on which W becomes trivial, is Stein. So sort of all the pieces that we saw in the example with an integral variation of Hodge structure, except now there's no variation of Hodge structure, it's just a complex locus, and no integral structure, more or less. Okay, great. And then this was generalized at work of Eyssidieux Katzarkov. So bad at locating people. Oh, there, Lamille, Tony, who I don't think is here yet, and Ramachandran, to show that if the fundamental group admits a faithful complex representation, then the universal cover is holomorphically convex. Okay. The main difference between this and this being there's no semi-simplicity assumption on the representation anymore. Now we're including the non-semi-simple case. Although we have lost the existence of this map X to Y, where the local system becomes large, which maybe I didn't say it, is what's called the Shafarevich map for the local system B. Okay, cool. So let me give you just kind of a super cartoony idea for how these proofs use ideas coming from non-abelian Hodge theory. Again, I'll say more details in a little bit, but the idea is you start off with a local system B. It's just a local system, just a complex representation of the fundamental group. And on the one hand, you find some, using non-abelian Hodge theory, some complex variations of Hodge structures that have finite monodromy on exactly the same subvarieties that V is finite monodromy. So among all subvarieties of X, you can look at the one along which V is finite monodromy, and you're going to find some complex variations of Hodge structures that also have finite monodromy on those subvarieties. And similarly, we're going to find some Q local systems, some local systems that have a Q lattice that have finite monodromy on the same subvarieties as V. Okay? Now, complex variations of Hodge structures have period maps. And so on the left-hand side, we'll get a foliation, which is somehow detecting subvarieties along which V is unitary. And using non-Archimedean harmonic theory, you can similarly kind of produce a foliation which detects when a subvariety has a property that V restricted to it has an integral structure. And then unitary plus integral means 5. So if I can sort of do both of these things and argue that these sort of the foliation I get by putting the two together is algebraically integrable, then I have produced somehow by integrating that foliation, I produce a map which contracts exactly the subvariety along which V has finite unitary and integral. That's sort of the idea behind the proof. There are, of course, some there's some hoops to jump through. Okay, so that's a summary of the case when X is smooth projective. But what about quasi-projective X, which was never sort of within the scope of Shafarevich's original question? Okay, well, let's first do a very easy example to show that we shouldn't expect too much. If X is the affine plane minus the origin, okay, it's simply connected, but it's not holomorphically convex. Okay, it does not emit a proper map to the Stein space. Which may seem discouraging, except the way I've been selling it, holomorphic convexity and Steinness, what the important part may be is that they have lots of global holomorphic functions. So A2 minus 0 is not affine, but it is quasi-affine. It's an open subset of the affine space, and therefore it still has lots of global holomorphic functions. So this kind of gives a hint, maybe, at what we should expect in the general case. And going back to the case of variation of Hodge structures confirms this expectation. So let's go back to the case where X supports a integral polarized variation of Hodge structures. And now let's not assume X is smooth projective. X is just some quasi-projective variety. Okay, so we still get a period map, a sign map for this variation of Hodge structures. And a result of Griffiths tells us that this map phi can be relatively compactable. In other words, it can be embedded inside a proper map. Okay, so it can be embedded in a proper map, so the analytic image still makes sense. We can still talk about Yn as an analytic variety, and then results. I should have said at the beginning. This is about joint work with Johann Brunebarbe and J. Tsimerman. And other joint work with them from a number of years ago shows that, in fact, this image is algebraic using some techniques from omenality, in particular omenal-Gaga. And actually, even better, in the case of a pure variation of Hodge structure, this image Y is quasi-projective, which had been conjectured by Griffiths. Okay, so this tells us the kind of shape that a theorem should take addressing this Shafarevich question in the quasi-projective case. So now let me state it. Here's the theorem. Let X be a normal algebraic space. It doesn't even have to be quasi-projective, just a normal algebraic space. And V a complex local system on X. There's a unique algebraic map, X to Y, meaning it's living in the category of algebraic spaces, which has the property that the local system V is pulled back from Y, and the local system on Y is both large the sense that we've described. It has infinite monodromy on every subvariety, and non-extendable, meaning it cannot be extended to any partial compactification. So this uniquely determines a map. That's not so hard to see, but in fact, such an algebraic map exists. So we can always, somehow, like I was saying before, given any representation of the fundamental group, you can always distill out all the subvarieties on which the local system is uninterested. Moreover, and this is kind of reminiscent of what I said on the previous slide about the pure case, the image is quasi-projective. If B is a semi-simple local system, then this variety Y is quasi-projective, which is kind of cool. It's saying that as far as complex algebraic varieties go, the geometry of semi-simple local systems is entirely contained within quasi-projective. All of that comes from quasi-projective. And finally, just as in example 2, the minimal cover of Y on which this local system becomes trivial is Stein. Okay, so we get all the same conclusions. Okay, so as a corollary, just as in the previous theorems, if the fundamental group admits a faithful complex representation, you have a local system with faithful monodromy, then the universal cover is quasi-holomorphically convex, meaning it's a Zariski open, a dense Zariski open in a holomorphically convex space. And if pi1x admits a large representation, right? So that's a local system, a large local system, meaning on every subvariety it has infinite image. Then the universal cover is quasi-Stein, meaning a dense Zariski open inside of the Stein. So in both cases, once again, we're getting sort of the existence of lots of local holomorphic functions. So it's sort of a kind of fun corollary that's easy to think about is the following. What we're saying is that if you have a normal algebraic space whose fundamental group admits a representation of infinite image, then the universal cover has a non-constant local holomorphic function. Very straightforward consequence of this corollary. Okay. Let's check the time. Cool. Okay. So now we get to the point of the talk where I tell you what I'm not going to be talking about. So there's a lot of pieces to the proof of this theorem, I mean the kind of main strategy is the same strategy as the proof in the smooth projective case by Eyssidieux Pantev Katzarkov Pantev Ramachandran. It's just that kind of non-abelian Hodge theory, the presence of boundary gets much more complicated, but a lot of work has recently been done, particularly by starting with Simpson and then Machizuki and many other names. I'm going to forget if I try this. So let me tell you the parts of the story I'm not going to talk about in the interest of time. So way back in the slide where I gave you the sort of cartoon idea for how to use, you find complex variations of Hodge structure, then you find Q local systems that each give you a type of foliation. The integral one is what's called the Katzarkov foliation, and Eyssidieux proves that those are integrable in a certain situation. In the projective case, and then we prove it in the quasi-projective case. I'm not going to talk about that, so that's a whole other story. That is the sort of non-Archimedean harmonic theory. I'm not going to talk about it because it's not part of this work, but I do want to mention that the construction of the Shafarevich map, that map X to Y that I've been talking about in the semi-simple case, was done analytically, independently by Brunebarbe and J. And so another part of the story that I'm unfortunately not going to talk about is how you algebraize those analytic constructions. And just as in the case of the period map of an integral variation of Hodge structures, this is where the sort of minimal techniques come in. Okay, so you algebraize these these analytic constructions of Shafarevich maps X to Y that you get using sort of period maps of complex variations of Hodge structures. You know, you use the minimal method, so you use minimal Gaga, so that was proven a while ago. The sort of new piece is minimal Stein factorization, which is actually really fun, but again, I won't be able to talk about it today. I'm happy to talk about some other point during the week. Just a short, I don't know. One thing to say, which is kind of fun, is that, you know, if you're trying to prove Stein factorization, you've been proving Stein factorization in different categories for decades. So there's a whole machine for doing that. Unfortunately, it uses cohomology, which is either poorly behaved or not yet understood at best in the minimal category. So we had to sort of go back and read Stein's original papers to see whether the proof he gives, which is not use cohomology, because that's the proof of Grauert, would apply in the situation, and that also does not apply in the case of minimal geometry. So this is sort of a new proof that somehow uses, well, now I'm talking too much about it, but it sort of uses the geometry of curves. Okay, so let me not get into that. Okay, so what I do want to spend the rest of the time talking about is this step of the proof where, starting with a complex local system, just a complex representation of the fundamental group, how you find variations of Hodge structures. Okay, and this is one of the sort of main pillars of non-abelian Hodge theory. This is sort of what Carlos proved, you know, was famously demonstrated at the very beginning. So let's start with some notation. So curly MB of x comma r is going to be the moduli set of local systems of rank r on X. Okay, so this is just, you take representations on a fixed vector space, that's just Holmes from pi1 and digit R, that's an affine algebraic variety, and you mod out by the conjugation action as a stack. Okay, the B is for big. And there's also there's a core space, which is the GIT quotient constructed by Mumford, and we'll call that non-curly MD. Okay, and its points correspond to semi-simple local systems. Okay, so here's an idea. So this curly MB has tons of structures. This is sort of the whole apparatus of non-abelian Hodge theory. And V has no structure, because it's just a random complex local system. So let's not think about V. Let's think about a slightly different gadget, which is the subset, which I'll call V shaf, which is sort of, you can think of as the Shafarevich closure of V, as all local systems that have finite monodromy on exactly the same subvarieties that V is finite monodromy. Yes, it's the same idea that I mentioned briefly before. Okay, and the point is that what is this locus? Well, it's just a big intersection of pullbacks of the trivial local system under the pullback map to some algebraic variety. Confusing for me to think about because it's the inverse image under the pullback functor. But basically, you take all algebraic maps for which V pulls back trivially, and then you look at everything that pulls back trivially and take that intersection. Okay? And all the structure that curly MB has is sort of compatible with these pullback maps for algebraic varieties. So this big intersection, which of course contains V, but in general will contain much more, has all the structures that curly MB had, and it has the same Shafarevich map, in the sense that by construction, these local systems are all finite monodromy on the same local system, that on the same subvariety that V has finite monodromy. So we may as well try to take these locals, we may as well replace V, this collection of locals. So we think of this V, this Shafarevich closure, as being sort of the non-abelian Hodge substructure. And you can, or at least we can define what that means precisely, but I'll stick to calling it V shaf. But everything I'm about to say will apply in general to an appropriately defined non-abelian Hodge substructure. That stuff. Okay, so what do we get? What the, you know, I elliptically am talking about has lots of structure. But what are those structures and what are their consequences? Well, here's one extremely important consequence, which is new to the quasi-projective case. So this is a result of Eyssidieux and then we prove an independent way. This Shafarevich closure is a Q-bar bialgebraic, or really absolute bialgebraic, in both the Betty stack that I defined and the moduli space of flat vector points, which also has a natural algebraic structure. And the two are analytically isomorphic by Riemann-Hilbert, not algebraically isomorphic. But these non-abelian Hodge substructures are algebraic defined over Q-bar in both. Okay, and that has the important consequence that local systems with quasi-unipotent local homodromy are Zariski dense in all non-abelian Hodge substructures, in particular inside of the Shafarevich closure. Okay, so this is extremely important because in non-abelian Hodge theory, the presence of boundary, the theory is systematically much simpler in the case of quasi-unipotent monodromy, but sort of as the eigenvalues of the residues drift away from the roots of unity, they become very complicated because they start mixing up. And so being able to just focus on the local systems with quasi-unipotent local monodromy is really an important step. And we're going to basically use it at every step henceforth. Okay, so what else do we need? Well, again, going back to the work of Carlos, there's a real analytic isomorphism between the moduli space of local systems and the moduli space of Higgs bundles, semi-stable Higgs bundles. So when there's boundary for a curve, we sort of use results of Simpson-Machizuki and a little more argumentation to show that this extends to a homeomorphism when you look at local systems with unipotent local monodromy. The difference between unipotent and quasi-unipotent is not so big. So really you should think of this as saying you get this non-abelian Hodge correspondence homeomorphically for quasi-unipotent, for the quasi-unipotent local monodromy. Now again, so one of the main structures that the space of Higgs bundles has is it has this algebraic GM action that Carlos shows has fixed points, which are exactly the sort of Higgs bundles associated to variations of Hodge structures. Okay, so this allows us to, take, by transferring this GM action to the other side, where it's just topological action, it allows you to, starting with any local system, follow this C star flow until you get to a local system underlying a variation of Hodge structure. The conclusion is that every component of this V shaft, the Shafarevich closure, has a point which underlies a variation of Hodge structure. Okay, so we have found some variations of Hodge structures. They just might be pretty sparse inside of V shaft. They might, if V shaft is irreducible, there might just be a single one that we produced. Okay. Well, how do we see all of the V shaft from just a single point? Well, we look at the universal deformation. This again, in the projective case, is due to work of Eyssidieux and Carlos. So if you take a local system underlying a variation of Hodge structure, this is a super cool fact. The universal deformation of that local system inside of the steady stack, the formal universal family, naturally underlies a pro-variation of mixed, emphasis on the wrong thing, a pro-variation of mixed Hodge structures. Okay, and this non-abelian Hodge substructure, V shaft, is kind of a quotient object in this category. Okay, so the universal deformation of V just inside of this substack V shaft is also a pro-variation mixed Hodge. So the conclusion is that even if our Shafarevich closure only had a single variation of Hodge structure point, the whole formal deformation at that point lives in the sort of Hodge world. It's a variation mixed Hodge structure. I didn't say the idea of proof. So why, how does one prove this? Well, we prove it a little differently from how Eyssidieux and Simpson prove it. Basically, the observation we use is that Zucker, going back to work with Zucker that was already mentioned, but then more generally by Plato, the cohomology groups of the endomorphisms of the local system, the endomorphism of the local system, has a natural mixed Hodge structure. And those are the deformation and obstruction spaces of the Betty stack. Okay, so if you show that the obstruction sort of takes values is always a Hodge class, then it's which it is, then it's believable that somehow the whole deformation functor is governed by variations of mixed Hodge structures, which it is. Okay, anyway, so the point of all this is now you get some points that underlie variations of Hodge structures. The universal family of those points are mixed variations of Hodge structures. And so we produced a bunch of mixed variations of Hodge structures, which have the property that their period maps contracts the entire locus that we want to contract, in the sense that all of the local systems in V shaft become trivial if I look at the period maps of these variations. Okay, so that's a lot to throw at you. And again, I just want to give you an idea of the sort of pieces that are involved. There's a slight problem, which is that curly M is not non-curly M. Okay, so going back to this list of consequences, A and C are very much about the stack, but B is importantly not about the stack. B is about the core space, okay? Because the GM action does not easily lift to the stack. It's not, in some sense, naturally lift to the stack. And okay, well, there's some issue there because somehow, by C, we get this super nice structure on the sort of formal local ring at any point underlying a variation of Hodge structure, but we don't get that until we sort of, under the C star action, arrive at the limit point. And we can't do that limiting process on the stack because by part B, that only lives sort of on the core space. It only lives in the world of semi-simple local systems. So that is a problem that needs to be addressed. And luckily, Carlos has already thought about this. I think it's a good, at least my experience is, a good rule of thumb in non-abelian Hodge theory is if you're stuck on something, it means Carlos figured it out 10 years ago. If you're not stuck on something, it probably means he figured it out 20 years ago. So you should read his papers, is the point. Okay, so what is the solution to this problem? Well, Simpson proves that the C star fixed points of this Betty space underlie variations of Hodge structures. So it's supernatural to ask the following fill in the blank question. C star equivariant what's are variations of Hodge structures? Because then maybe we can interpret every point of the moduli space of local systems as those blanks, and then the C star fixed ones correspond to C star equivariant ones, and those will be variations of Hodge structures. And the way we fill this in, again, as Carlos introduces, this variations of twistor structure, which I'm certainly not going to define other than this little SAT word problem. Okay, so C prime. So now we can upgrade C. And again, this has been first treated by Carlos, and then we do it in general. So for any semi-simple local system, I maybe should have said with I forget now, but let's assume quasi-unipolar Pantev, because why not? The universal deformation underlies a pro-variation of mixed twistor structure. Okay? This kind of new notion that we've introduced that so now if you have a C star equivariant such thing, it recovers the pro-variation of mixed Hodge structure that we had before at the C star fixed points. And similarly, the formal universal deformation inside of this Shafarevich closure V thing, this non-abelian Hodge substructure, is a quotient in this category, this enhanced category. Okay, the idea of the proof is the same idea as before, because we now need to equip the deformation and obstruction spaces with the relevant structures, which are now mixed twistor structures instead of mixed Hodge structures. And Machizuki has done it. Okay? This sort of Machizuki carries out sort of the analog of Saito's work in the world of mixed twistor variations of mixed twistor structures. Okay, so sorry, before I give it, well, let me give this corollary. So the corollary now is, so this corollary is going to look like what we had before. I don't expect anyone to have noticed this, but now, you know, in B, it's B shop with an S Roman, and now it's a B shop with an S calligraphic. So every component of this Shafarevich closure on the stack has a variation of Hodge structure. And in particular, we deduce as a corollary the fact that every component of the moduli stack of the local systems has a variation of Hodge structure point, which is, as far as I know, is new, because there are components of the moduli stack that are generically non-semi-simple. So they just disappear completely when you go to the core space. And so you can't apply necessarily, or you can't easily apply the sort of the usual yoga, the usual non-abelian Hodge theory arguments just on the core space. Someone can tell me if this was known before, but I couldn't find it. Okay. Great. Perfect. Okay. Thank you so much.
Yeah.
Okay. Like I said, this is obviously an extremely poor slide, but I wanted to explain how these having this sort of mixed twistor structure at every point of the Betty stack actually allows you to show that in a certain sense you can lift the C-star action to VE shaft. Okay, and I'll try to get away without a pointer. But this is the point. So sorry, I wrote M dole, but what I meant was M sub BH. Okay, so this is what's called the Deligne-Hitchin space, and this is the phase of lambda connections. Okay, so these are flat vector, you know, sort of like flat vector bundles, except in the Leibniz rule, the differential term has a lambda in front of it. So for lambda equals 0, you get a Higgs bundle, and for lambda equals 1, you just get the normal definition of a flat vector bundle. So this is a space that lives over P1. That's what this map, this rectangle is supposed to be the space of lambda connection. When it maps down to P1 by a lambda, and the fiber over 0 is the Higgs bundle space, and the fiber over 1 is the flat vector bundle space, and the fiber over infinity is sort of the anti-holomorphic. Okay, so this space is kind of the analog in the smooth projective case. This is sort of the twistor family that goes back to Hitchin. In the non-projective case, a non-smooth projective case, so if either there are singularities or there's boundary, then this doesn't fully have the interpretation of a sort of twistor space, because it's sort of a mixed twistor space. You know, the difference is that the deformation rings have pure twistor structures in the sort of smooth projective case, but they don't have pure twistor structures in the general case. Anyway, okay, so this space has these preferred sections corresponding to the family of lambda connections you get from the harmonic metric on a flat vector bundle that's in the compact case and then Machizuki in the non-compact case constructs. Okay, so you get these natural sections, which again you should think of in the usual construction of a twistor family as being like the constant sections. And they have sort of two ways to deform them. Okay, so you can deform them in a non-holomorphic way, preserving the harmonicity condition. So if you only stay within the world of sections that come from these harmonic metrics, it gives you a red deformation that I hastily drew over there. But there's also a GM action on the space, which comes from just scaling the connection, which covers the usual scaling action on P1. And if I apply that GM action to my section, that gives me this blue section, which may no longer be the one associated to our harmonic metric. Okay, so I have these two ways of deforming, and it gives me a GM action and a C star action. Because the GM action I just described, the C star action is sort of I look over the zero, I scale the Higgs bundle, and then I look at the corresponding section coming from a harmonic metric. Okay? So the C star action is very much not holomorphic, and the GM action is holomorphic. So you know for free that this V shop is GM stable, and you want to show it's C star stable. That's what all of this boils down to. On the level of the stack. Okay, and then the point now, this is where we see that where it matters that V shop is a sort of sub-mixed twistor space, is that because it's a sub-mixed twistor space, you conclude that the C star flow, if you look at the C star flow in the normal bundle to this V shop, it lives in a sub-bundle which is just a bunch of copies of O1. Okay, so the relevant normal bundle for looking at how the red deformation is deforming outside of V shop lives in some power of O1. So if I check that it stays in V shop at 2 points, then it stays in V shop everywhere. Okay, because a section of O1 which vanishes at 2 points vanishes everywhere. Okay. Well, the GM and the C star actions coincide over 0 and infinity. That gives me 2 points along which the normal part of the C star flow is 0. And therefore you conclude, because V shop is sort of a mixed twistor subspace, meaning its deformation ring is compatible with the mixed twistor structure, that the blue deformation must coincide with the red deformation everywhere. And therefore, from the GM invariance of V shop, you get the C star invariance, which just means that these sections corresponding to harmonic bundles, how to say, this V shop is saturated with respect to these sections corresponding to harmonic. Okay, so that's again, I want to throw at anyone, even people who are sort of well versed in non-abelian Hodge theory. But the conclusion then is that the conclusion is not exactly, but it's basically saying that on the level of the stack, you can do the C star limiting process, and therefore on the stack produce variation of Hodge structure. Okay, so went through that a little more quickly than I meant, but I think I am done. It's been a long day. I can't advance that. So thanks.